name is Clotilde Philippe, and I'm a PhD student at ENSCR under the supervision of Yann, Trolez and Loïc Lemière. So today I'm going to present you my PhD work about the synthesis of Ynamide, formation and study of fluorescent tetracyanobutadienes. So first of all, TCBDs are the product of the reaction between an electron-rich alkyne and tetracyanoethylene, so short for TCNE, by a 2+2 cycloaddition, then a retroelectrocyclization to give this TCBD motif. So this reaction have been known from now several decades, and a large number of electron donating group have been tested and shows that the reaction works quite well with ferrocene, aniline, thiophene, and so on. So TCBDs are interesting because they have exceptional optical properties. So they have intense linear and nonlinear absorption, but they are generally non-luminescent. There is only a few examples that show luminescence in solution at room temperature, and they have quite low quantum yield, less than 4%. The reason why they are generally non-luminescent is due to very efficient non-radiative deactivation. This was proved by calculation for those two compounds. So we can see that we have a deactivation by the rotation of the TCBD. So our group is interested in the reaction between Ynamides, so this compound, and TCNE to form this new kind of TCBD. So we were able to show that this reaction works quite well with a lot of substrate, even if with some electron withdrawing group we have a lesser yield, but we can increase the yield by increasing the amount of TCNE. So during the investigation of this reaction, we were able to see some unexpected luminescence properties. So you can see that for this compound, we don't have any luminescence of the solution, which is a mixture of cyclohexane and dichloromethane, but we have luminescence of the crystals. For this other molecule, we see that we don't have any luminescence in dichloromethane, and by increasing the amount of cyclohexane, we have an increase of the fluorescence, the quantum yield. So we see that this kind of TCBD have a luminescence sensitive towards the environment. So my project is to synthesize more TCBD from Ynamide bearing diverse fluorophore on this position. So I've worked with perylene, anthracene, and some derivative from fluorine. And we are trying to understand their luminescence behavior, which is luminescence in powder, but also in solution. So first of all, let's talk a bit about the synthesis. So for the perylene TCBD, we decided to do the formation of the Ynamide in Evanus condition. So to do that, we started the synthesis with the perylene, and we did form the aldehyde on this position with 29% yield. And then we form our gem de Beaumont vinyl with 97% yield, which is the starting material for the Evanus condition, which is a copper catalyzed reaction that gave us our Ynamide with 50% yield. Then we were able to form our TCBD with 71% yield. So another example is the anthracene TCBD. So here we are working with Thun condition for the formation of the Ynamide. So we started the reaction by a Sonogashira coupling on the 2-bromo anthracene with 86% yield. Then we did the deprotection of this alkyne with 5% yield, and we then form the bromo alkyne with 78% yield, which is the starting material for the Thun condition, who is also a copper catalyzed reaction that gave us our desired Ynamide with 71% yield. So when we put this Ynamide in reaction with TCNE, we didn't get the desired TCBD, but the product of the disalder on the anthracene core. And by adding another equivalent of TCNE, we did form the TCBD, but we still had this Diels-Alder reaction on the anthracene core. We also showed by reacting our Ynamide with 5 equivalent of TCNE, we can directly get this compound with 73% yield. So now we try to recover our anthracene core. So to do so, we try to do retro Diels-Alder, and we did put this compound in dioxane at 80 degrees, and we did observe the liberation of TCNE, but the equilibration of this reaction does give us only 14% yield for the anthracene TCBD. So we decided to add some scavenger to catch the released TCBD. So we choose this aniline compound, and by catching the TCNE and form this TCBD, we were able to get our anthracene TCBD with 76% yield. So to understand better this reaction, we also made another example with the diphenylanthracene TCBD to see if we have also a Diels-Alder or not. So we started with this diphenyl bromoanthracene and did the Sonogashira coupling with 88% yield, and then the deprotation and the bromination to be able to perform our Ynamide with 89% yield. So then by adding 1 equivalent of TCNE, we directly get our TCBD. Due to the steric index of the 2 phenyl group, we don't have the Diels-Alder on the anthracene core. So the mechanism for those 2 reactions on the anthracene were deciphered by theoretical calculation by Trevor M. So I was able to synthesize a large amount of TCBD, so with pyrene, perylene, anthracene, phenanthrene, triphenyl, and some derivative from the fluorine. And I did the UV visible analysis on this compound, but also the measurement of the fluorescent in solution and in solid states. So for the UV visible spectrum, we can see that by changing the fluoro4 on the TCBD, we can modulate the maximum of the first band absorption. So we can go with the triphenyl compound for 440 and to 540 for the pyrene and anthracene, and up to 640 with the perylene compound. For the fluorescence property, we can also modulate our emission maximum by changing the fluoro4. As you can see, with the fluorenon, we have an emission at 534, and with the phenanthrene, we can go up to 648. Which is also quite remarkable is the quantum yield of this triphenyl TCBD, which is at 8%. And it's, to our knowledge, the best yield ever reported for fluorescent TCBD in solution at room temperature. We did also the measurement of the fluorescence in powder. And we can see that by changing the fluoro4, we also can modulate the emission. And this time in solid state, we can have an emission up to the near infrared with the pyrene and the perylene TCBD. So to conclude, a large number of fluorescent TCBD have been synthesized. Their emission in solid states and in solution can go up to the near infrared region. We can modulate the emission maximum by changing the fluoro4, and we can have a quantum yield up to 8% in solution at room temperature. The next step to understand this phenomenon will be to do more analysis like time resolved fluorescence and transient absorption, which will be made in collaboration with Antibri and Nathan McLenagan in Bordeaux. So I will also like to thank all the people that have worked with me on this project, but also you for your attention. Thank you.
Thank you very much, Clotilde. So we will take only 1 question, and if there are more questions, you will be able to ask them at the end of the lecture by Phil Castellano. So are there any questions? So if not, Clotilde, stay tuned, and maybe there will be question in the chat or at the end of the lecture.
Thank you.
So now, Phil, you can unmute yourself and you can start to share your screen. Yes. So I will make only a very brief introduction.